reviewing this paper. So we're just going straight to figure 1. I'll just comment along as we go.
Imagine living with a condition like motor neuron disease. It affects, 64,000 people worldwide, something like that, where your ability to move, even to communicate, is drastically limited. It's a profound challenge.
It truly is. Daily life becomes incredibly difficult.
But what if there was a way, like a direct connection from your thoughts to the world outside?
That's exactly the idea behind brain-computer interfaces, BCIs.
Right, BCIs. They promise this direct link, brain to external device, offering a real path to improving quality of life. A big promise.
A huge promise, absolutely. But when you look at the tech we have now, well, there's some pretty big hurdles still.
Yeah.
Current BCIs, they sort of fall on a spectrum, how invasive they are, how easy they are to use, and frankly, none are perfect.
Go on.
So on one end, you have the really invasive stuff, electrocorticography, ECoG, and these penetrating arrays. They need major surgery, a craniotomy, opening the skull.
Yeah, that sounds intense.
It is. And there are risks during the operation, obviously, but also long-term issues like scarring around the implant, damage to the brain tissue itself, which ironically can make the signal worse over time.
Okay, so high risk. And the signal might not even last. What about less invasive options?
Well, there's traditional scalp EEG. You've probably seen the caps with all the wires. Much less risky, no surgery.
Right.
But let's be honest, they're not very practical for everyday life. People find them cumbersome, kind of clunky looking, takes ages to put on and take off, and the signal stability isn't always great. It's just not a discrete, long-term solution.
I can see that. Not something you'd want to deal with daily.
Exactly. And then there are newer sort of minimally invasive approaches like endovascular stent electrodes. They go in through blood vessels.
Okay, that sounds clever. Less invasive than brain surgery.
In theory, yes. But they have their own drawbacks. Often poor spatial coverage. You can only really put them near large blood vessels, which limits where you can record from.
Ah, I see.
Plus, once they're in, they're generally non-removable. And they carry risks similar to other stenting procedures like blood clots, thrombosis.
Okay, let's unpack this. It sounds like there's a clear need for something in the middle, doesn't it?
Yeah.
Something minimally invasive that gets good signals, but avoids the big surgeries or the daily hassle of caps.
Precisely. We need a method that could genuinely enable widespread, long-term BCI use.
And that's exactly what our deep dive today is all about, exploring the potential of Sub-Scalp EEG based on some really interesting recent research.
You've hit the nail on the head. Sub-Scalp EEG, sometimes called subgaleal or subdermal, looks like a really viable solution to this exact problem.
So, Sub-Scalp, under the scalp.
Exactly. The devices are implanted under the skin of the scalp, not on the skin like an EEG cap, and not inside the skull like ECoG or penetrating arrays. It's kind of a sweet spot.
Interesting. What are the advantages then?
The study we're looking at highlights several key ones. First, and maybe most importantly, the risk is much lower. No brain surgery, no vascular surgery needed for implantation. That's huge.
Definitely a big plus.
And the user experience, dramatically better. Once it's implanted, it's discreet, hidden under the hair. You get improved signal stability compared to scalp EEG. And crucially, no daily putting it on and taking it off.
That alone sounds like a game changer for daily use.
It really is. Then there's versatility. Because they're under the scalp, you can actually place these electrodes pretty much any way needed on the skull. You can access brain regions that those endovascular arrays just can't reach because they're tied to where the big blood vessels are.
Okay, so more flexibility in targeting brain areas.
Right. And another critical point, they're removable. If you need an upgrade down the line or if there's an issue, they can be taken out relatively easily.
That's important for long-term tech.
Absolutely. And we actually have a long track record showing chronic implantation of electronics under the scalp is safe. Think about cochlear implants. They've used that principle for decades.
I'm not sure where the cochlear implant stuff came from. Cochlear. Okay, the cochlear implants actually mentioned in this paper. Okay, the cochlear implants are not removable. I mean, yes, they are. It's not as easy as a podcast has made it sound. So it's not as removable as you might think.
Good point. Like a cochlear implant, but for brain signals.
Sort of, yeah. And Sub-Scalp EEG isn't entirely new in concept either. It's already being used clinically for long-term seizure monitoring, and it's showing promise there too.
Okay, this is sounding really promising. Lower risk, better usability, flexible placement, removable. It ticks a lot of boxes. But here's where it gets really interesting for me. While the general idea sounds great, the big question this study tackled was, How does the specific depth of these electrodes beneath the scalp impact the signal quality, especially for BCI control?
Yes.
And how do they actually stack up against those gold standard technologies?
Yeah, I have to mention it. There's the thing in the paper. It says the safety of chronic implantation of electronics beneath the scalp has been demonstrated by cochlear implants around the world over decades. So okay, now I get it. So what they're talking about is not the actual cochlear implant array, is the device, under the skin. So yeah, it's a very odd example. Yeah, and the robot. I thought it's just hallucinating on me, but no, it's picked it up from the paper. It's just it's not just that sentence. It's just weird. It's not a great analogy, because when you're thinking cochlear implantation, you're thinking the electrode array in the inner ear inside the cochlea, whereas here we're talking about electrode arrays located just under the skin. So very, very different, like that kind of positioning there. Very different. So that analogy is odd, but yeah, let it slide.
Like ECoG.
That was precisely the core question. How good is the signal really? And they designed a very careful study to figure that out.
How do they do it?
They used an animal model, 6 female Corriedale sheep.
Sheep? Why sheep?
Good question. Their skull size and the blood vessel structure are actually quite similar to humans in relevant ways. So they make a pretty good model for this kind of research.
Okay, makes sense.
And the clever part was the sequential electrode placement. In each sheep, they put electrodes at 5 different depths or locations, allowing a direct comparison, like for like.
5 locations, what were they?
Okay, so first, endovascular. An array placed inside a blood vessel, the transverse sinus in this case. Second, periosteum. Electrodes just sutured onto the periosteum, that's the thin tissue layer covering the skull bone.
Right.
Third, skull surface. Here, they actually removed the periosteum and screwed electrodes directly onto the bare skull surface. Fourth, peg electrodes. This involved making a small shallow hole about 4 millimeters deep in the skull and embedding the electrode partially within that hole.
Embedded in the bone itself.
Partially, yes. And fifth, the benchmark, ECoG. An array placed in the subdural space right on top of the visual cortex, so closest to the brain surface. That was their gold standard comparison.
Got it. So endovascular, on the tissue, on the bone, in the bone, and on the brain. A clear progression of depth.
Exactly. Then for each location,
Yeah, I can just say, it's the naming conventions for these things are super weird. Well, because you can have sub and peri. So essentially sub means underneath something and peri means above something. So then in each case you can have 2 different names. So it can be, so if this is your skull, you can have whatever, periscalp or sub-scalp. If you have periosteum, then you have, peri is above the ostium. But then you can have it, so the naming, I'm just saying the names can be quite confusing. So just, don't worry about it. But yeah, you see where the positioning is. Now with the peg electrodes, there's, so we did studies on this as well. Yeah, the actual positioning within the bone is can be quite important as well. So in this case, at least the drawing, seem to be going like halfway. Those lens, by the way, I think it's only for when that connector looks like a very old school connector. I don't know if it was custom made or something, but I think the lens there, I'm not sure. There could be a chance, but I don't think it is. It could be that it's used to actually adjust the height, but I actually think that the varied length there is to make it easier when you put a wire, connect the wire to it, so you reduce the chance of the wires shortening together. But yeah, I don't know, it's hard to tell, but it's just minor. Not minor, but a whole other thing.
They flashed a light in the sheep's eyes to generate visual evoked potentials, or VEPs. That's a standard way to measure the brain's electrical response to a visual stimulus.
Okay, so stimulate the brain, then measure the response at each electrode depth.
Precisely. And they focused on 2 key metrics for signal quality. First, the VEP signal-to-noise ratio, or SNR. That basically tells you how clear the brain's response signal is compared to the background electrical noise. Higher SNR means a cleaner, more usable signal.
Crucial for BCI, I imagine.
Absolutely critical. And second, maximum bandwidth. This measures the highest frequency of brain activity they could reliably record. They were particularly interested in the high gamma band, typically above 70 hertz.
Why is high gamma important?
Because high gamma activity seems to be really rich in information that's useful for fine-grained BCI control. Think controlling a cursor smoothly, not just clicking a button.
Okay. So higher frequencies potentially mean more sophisticated control.
That's the idea. And alongside the animal experiments, they also built a computational model of the sheep's head. This let them simulate the electrical fields and explore how things like different tissue layers and electrode distance affect the signals theoretically.
All right, so a really thorough approach, animal experiments across different depths, key signal metrics, and computer modeling. After all that meticulous...
Yeah, by the way, if the model, whatever the head model is available in a public domain, we are more than happy to look at something like that. Yeah, because we don't want to be implanting stuff into animals for obvious reasons, mainly because it's very messy. But if there is a model available, if it isn't available, maybe we can ask Gemini or another AI to generate a model like that, or approximate like a head with electrodes on it. That's something we definitely can look into.
What were the most important takeaways? What did the signals actually reveal? What truly stood out for you?
Well, the results were pretty illuminating. The absolute standout finding, the real aha moment, came from the PEG electrode.
The ones embedded in the skull.
Yes. Let's break down the SNR first. As you'd probably guess, ECoG, being right on the brain, had the highest signal amplitude and the best SNR. It confirmed its gold standard status.
No surprise there.
Right. And on the other end, the periosteum electrodes just lying on the tissue over the skull had the lowest amplitude and the lowest SNR. The endovascular rays actually had similarly low SNR, comparable to the periosteum ones.
Okay, so placing them just on the outer tissue isn't great for signal clarity.
Not ideal, no. But here's the crucial part. The PEG electrodes, the ones partially embedded in the skull, achieved an SNR that was remarkably close to the ECoG gold standard. Statistically, there was no significant difference between them.
Wow. So almost as good as being right on the brain, but with a much less invasive procedure than a full craniotomy.
Exactly. That's a potentially huge leap. We're talking near gold standard signal quality without opening the duramater, the brain's protective layer.
That is significant. What about just placing them on the skull surface after removing the tissue?
That was interesting too. Simply removing the periosteum and putting the electrode directly on the skull surface more than doubled the median SNR compared to leaving the periosteum in place. So just getting direct contact with bone made a big difference. And embedding the PEG electrode further, while it did increase the signal amplitude slightly, it didn't significantly boost the SNR further compared to just being on the skull surface. So the main jump in clarity seems to happen once you get past that periosteum layer onto the bone itself.
Fascinating. So skull surface gives a big boost. PEG maintains that high quality.
Yeah, this figure is a bit confusing. It looks like the ECoG, which is the electrodes on the surface of the brain, produce like lower amplitude signal than the PEG and skull surface. But the reality is that, so those bars are absolutely important. This figure is this is quite common in scientific literature where, if it was a YouTube thing or on a website or something, you had to make absolutely, the focus should have been on these black markings there. So that's the amplitude and it specifies, I assume. So for ECoG, essentially that amplitude, whatever that millimeter, is actually representing 320 microvolts, whereas for a endovascular electrode, that's the electrode in the vein, that same height amplitude is only representing essentially 10 times less microvolt signal. But it's not clear from the left side. Essentially, the point is that the ECoG has larger amplitude signal. Just not a great figure.
What about the bandwidth? Could these subscalp electrodes pick up those important high gamma signals?
Yes, they could. And this was another really important finding. All the subscalp locations, periosteum, skull surface, and PEG were capable of capturing that high gamma activity above 70 hertz. Their maximum bandwidths were pretty high, ranging from about 120 hertz up to 180 hertz.
And how did that compare to ECoG?
ECoG and the endovascular arrays did show slightly higher median bandwidths, around 200 hertz. But, and this is key, there was no statistically significant difference in maximum bandwidth across all the electrode types when analyzed together. Meaning even the simplest subscalp placement just on the periosteum can still pick up those vital high-frequency signals needed for complex BCI control. You don't necessarily need to go deep or invasive to get that bandwidth.
That's great news for less invasive approaches.
Yeah, this figure is so bad on so many other levels. So yeah, now I understand what it is. So this is a visually evoked potential. So where the dashed lines are, there's some sort of very strong flash of light going into the eye of the animal, a sheep in this case. So the problem with this figure, though, that in endovascular you had these three flashes, essentially one having a strong response, one having a response before the flash even started, meaning it must be an artifact. So the animal is moving or something else is going on, and the third flash doesn't seem to elicit much of a response at all. ECoG is much better as expected, so you have like your the baseline is better, so you have like more quieter signal before the stimulation. When the stimulation occurs, you have this supposedly about 600 microvolts or so a response, which is quite large. This is the average response. So this is from one of the animals. Yeah, amplitude. Yeah, same for the skull surface. It just wasn't recorded like correctly. There was some artifact going on before the stimulation, before the stimulus. But yeah, I'm not sure what this figure meant to tell, except suggest some problems with the experiment, with the recordings. Not sure what's going on there. And this one, so it should have like a bar chart for this, essentially indicating that the ECoG had a much larger response, which is as you would expect, because the ECoG is closer to the brain, and other electrodes might have all sorts of other issues with them. Yeah, so the ECoG is just sitting on the surface of the brain. So yeah, not quite a fair comparison, isn't it? Yeah, well, because it's the most invasive as well, so let's just keep listening.
And the simulations, did they back this up?
Broadly, yes. The computational model agreed that ECoG would record the highest amplitude. It also helped confirm that physical factors like how conductive the tissues are and how far the electrode is from the brain activity really do matter for signal strength. It basically reinforced the idea that subscalp EEG is a very plausible, less invasive alternative.
So it seems we're getting powerful signals, clear signals, and the right kind of signals, high frequency, from these subscalp electrodes. But what does this all mean for the big picture, for the listener, for the future of BCI design, and most importantly, for the individuals who could benefit? What's the so what here?
That's the crucial question, isn't it? The so what is potentially enormous. This data gives us really clear guidance for designing the next generation of BCIs.
How so?
Well, it lays out the trade-offs. PEG electrodes give you SNR that rivals ECoG fantastic if you need super high fidelity control, but it does require making that small burr hole in the skull.
Right.
Placing electrodes directly on the skull surface gives you a massive signal quality boost over just putting them on the periosteum, and it's a simpler procedure than the PEG. Even the simplest approach, tunneling electrodes under the skin onto the periosteum, can still pick up high gamma, which might be perfectly adequate for certain BCI applications.
So designers can choose the level of invasiveness versus the signal quality needed.
Exactly. They can tailor the device and the procedure to the specific user's needs and the complexity of the task they want to achieve. And importantly, this study strongly suggests sub-scalp EEG is overall a more suitable approach than endovascular arrays.
Even though the SNR was comparable between endovascular and periosteal.
Yes, because subscalp offers so many other advantages. You can easily place multiple electrodes over different brain regions using tunneling from a single small incision, the removable, remember? And you avoid the serious risks and surgical complexity of implanting stents in brain blood vessels, which also really limits where you can record from.
Okay, that makes sense. Sub-scalp seems more flexible and safer overall.
Definitely. And this kind of data is exactly what's needed to move towards human trials and ultimately towards chronic in-home BCI systems. Systems that can genuinely empower people with physical disabilities, letting them interact with their environment and improve their independence.
In-home use. That's the real goal, isn't it?
It has to be. And think about this. If you have many people using these sub-scalp systems long-term, continuously streaming EEG data, you could potentially train incredibly sophisticated AI algorithms on that massive data set. Imagine reducing the time it takes to calibrate a BCI for a new user from weeks or months down to maybe days or even hours.
Wow, that would make the technology so much more accessible.
Huge difference. And we expect sub-scalp BCIs to offer better dimensionality of control compared to something like an endovascular array, which might just give you a simple click.
Dimensionality
meaning more complex, nuanced control. Because you can record from multiple brain areas with sub-scalp, you could potentially achieve multidimensional control, maybe even 3D control, like some non-invasive EEG studies have suggested.
So not just clicking, but maybe moving a cursor smoothly, controlling a robotic arm.
Exactly. Operating prostheses, wheelchairs, keyboards, computer interfaces, unlocking access to the internet, communication tools, environmental controls, employment opportunities. It opens up so much.
It really does.
And critically, because sub-scalp EEG is minimally invasive, it's potentially suitable for a much wider range of people than highly invasive BCIs.
How so?
Well, intracranial devices with their higher risks are often reserved for people with very severe, often life-limiting conditions. But sub-scalp, being lower risk, could be appropriate for individuals with, say, multiple sclerosis, cerebral palsy, spinal cord injuries, amputations, muscular dystrophy, even for stroke rehabilitation. People with longer life expectancies where the risk-benefit calculation looks very different.
That vastly expands the number of people who could potentially benefit.
It does. And that also improves the prospects for commercial development, making these systems more likely to become widely available. Plus, beyond direct BCI control, this kind of continuous high-quality EEG could monitor other things: pain, fatigue, stress, maybe even depression or sleep apnea, giving doctors valuable long-term data.
That's truly incredible. Thinking about the whole picture, while the study, acknowledges limitations, it was acute, not long-term implants, didn't directly measure spatial resolution. Maybe the overall potential it paints is just incredibly compelling. It really feels like it's about opening up a whole new world of interaction and independence, isn't it?
It absolutely is. That's the driving force.
So what's the next big hurdle then? Getting this from the lab, from these sheep studies, into someone's living room?
The core conclusion from this work is crystal clear. Sub-scalp EEG is a genuinely promising path forward. It's low risk compared to the alternatives. It's stable. It's aesthetically acceptable. It captures the crucial high gamma signals. And the PEG electrodes get you SNR comparable to the gold standard ECoG. It just makes a very strong case compared to endovascular or traditional scalp EEG for long-term use.
And the next step?
Human trials are the critical next step. We need to demonstrate long-term safety, stability, and real-world effectiveness in people using these systems day in, day out. That's the bridge we need to cross.
It's an exciting bridge to be building. Think about the profound difference this could make for so many lives. It's not just about enabling actions, is it? It's fundamentally about restoring communication, control, participation in life, all from the comfort and safety of home. What possibilities does this spark in your mind for the future of accessibility and just, human connection?
Yeah, there's so many there's so many things. So the stars there, obviously, I think so they indicate how significant the difference is. So one star should be very significant, and two stars there should be highly significant. So interestingly enough, there's no difference between what's essentially sub-scalp, which in this table in this figure they call periosteum, to endovascular, even though the endovascular is much more invasive. So if there's not significant difference between the two, obviously you go for the sub-scalp as opposed to the endovascular, because the very high invasiveness level. Yeah, it's good that they did the whole frequency spectrum. It's actually showing no difference between all the electrodes types. Yeah, I like the simulation bit. Yeah, based on the simulation, the ECoG should have had a much higher signal to noise or something, but it actually was not quite the case. This is across animals, right? Anyhow, we might be moving on. There might be a lot of noise in this data. Otherwise, yeah, if the model of the head is available public domain, we're more than happy to try something like that out ourselves. So don't forget to like, comment, subscribe, unsubscribe. Yeah, if you have any papers you want me to look at, go for it.